什么来？哦，YouTube video OK 啊。嗯，等一下我们要 end 在几点？现在10点，11点是11点50。我们要提早50分钟。嗯，50提早10分钟，因为下一个班要进来，他们要准备。嗯，因为不然那老师在另外就是等等等的。这做糖的，做糖都可以。像这样转，你知道是什么 bread 吗？什么 bread 啊？啊，呀，就一直做，一直做，一直做。啊，还是就是做那个 Christmas 的那个糖是吧？不是 Christmas 的那个糖，因为那个 Christmas 的那个糖，哦，每次有刷到。这个那是。早上课起不来，学生。早上的课那学生起不来，8点整起不来，4点也起不来。 有比过这些看过 Nox 的票，是我的那票，我们就做 Nox 的 FIPB 的，没有的。Not FIPB 应该不是啊，Not FIPB 要这样的，好的，会的到一般这个，整个还是整个哎，对对对对对，这些好。就是我看完那个光，到我的。多好哎！啊，是这样，应该是还没起来，没起来。非常就是嘛，就一样，common sense 啊，compliment，白色，白色，好冷的笑话啊，好冷的笑话，白色，如红色，如红色。比较好笑的话是，什么啊？如果是同一个作者写的，那就比较高。哎，有些老师不是这样的，你来我补习，我教你，学校教。没有讲哇，嗯，要被立为非法操作。是哦。Wait for another 1 more minute. Okay. Um. Right. So for today's first hour, we'll be having lecture. Second hour, we have Edmund to do some sharing session here. Uh, he will talk about topology. Okay. Topology in general, not general topology. Topology in general. How it relates his research, and then maybe share some experience of doing maps. Okay. Okay. Let's start for the lecture first. Okay, so let's recall two pieces of definition before we go into another two notion of compactness. So our first notion you should recall is the limit point. Okay, so how is a point in the topological space called a limit point? If for every neighborhood, open neighborhood, so there's an open set containing this axia, will intersect A. So if you want to talk about limit point of a set A, so you take the candidate limit point, look at all the neighborhood, okay, all the open set that contain X, it must intersect the set A some in some other point other than X itself. Okay, other than X itself, huh? So must be some other point in A. How about convergence here? So in a topological space, you also can look at sequence of points, okay, from that space X. So if we want to say that X converges, okay, to the point, the sequence converges to a point X here. If to each open neighborhood U, also we look at every open neighborhood UX here, such that there exists an N, a big N here for all little n greater or equal to n, Xn must live inside U. Okay, so um, meaning what? Meaning the tail, okay, the tail of this sequence here must live inside all neighborhood. Okay. Uh, so last time I already show you example why sometimes we don't call this X a limit point. Sorry, a limit, right? Usually in calculus, you call this convergent point called limit point, right? But if it is in non-Hausdorff space, you might have more than one such X. So usually when you only have one such X, we'll call it a limit. Okay, so there's a slight difference between these two definitions. Okay. Okay. Any questions so far? Okay, so let's discuss. So first, we'll do both of them together. So we'll define what is called a limit point compactness and a sequential compactness. All right. So we say that a space or a subset of a topological space here is a limit point compact. Okay, if for every infinite subset A, okay, of Y here, it has a limit point in Y. Okay. So when we talk about infinite subset here, we don't have idea of sequence. Okay, just there are infinitely many elements inside the subset here. And this infinite subset here we require them to have a limit point in Y itself. Okay, only then we will say that Y is a limit point compact. Okay, second, we say that subset is sequentially compact. Okay, so sequentially compact is the usual one you see in MA before. So if every sequence in Y, what happened? Nothing yet. X, X or Y. Okay, so every sequence in Y has a convergent subsequence. Okay, don't converge outside Y. Converge to a point in Y. Okay, and remember these two ideas here. Okay, so you see both actually involve the idea of infinity. So in first case, we have infinite subset of Y that has the limit point in Y. In second case, every sequence has a subsequence that converges. We don't require the original sequence to always converge, but it must contain a convergent subsequence. Okay, next sense? All right. Let's look at some example. Okay. I think this is your MA assignment. Is it true? Once you see this set, do you know what you want to deduce about this thing. What's the limit point here? Zero. Okay. So why the limit point is why zero is the limit point? What's the definition just now? You just recall, right? What's the definition of limit point? Every open neighborhood of zero must contain. Okay, definition first. Must contain what? Some other point other than zero in A. Okay. So if you build open neighborhood around zero, do you always intersect with A or not? Why? What property makes you intersect with A? Huh? Archimedean property. Okay, good. Okay, contain a limit point of A here. A. Okay, I think I named my A wrong, or A is correct. So the Y I'm looking for is this. So I'm asking whether this Y is a limit point compact or not. So A is an infinite subset, right? Okay. But the limit point is not inside Y. Okay, it's not inside the open interval here. So we say that the open interval 0, 1 is actually not limit point compact. Sorry? Square bracket for the Y. Square bracket for the Y. Oh, sorry. Sorry. Huh? Okay. Okay. So it's an open interval. Okay, so similarly, we can ask the question whether this open interval 0, 1 is sequentially compact or not. Okay. If to show sequentially compare, you need to check for every sequence. Okay, having convergent subsequence. If you want to show that it is not sequentially compact, find one. Yes. Okay. So I'm going to try and think about it. Sorry? Sorry? Again, 1 over n. Okay. So we look at the same sequence here. Well, I mean, sequence that build up from this infinite sequence, infinite set. So if we look at this sequence, this sequence has no subsequence converging to a point in 0, 1. Okay, converges, but it converges to point outside this subspace. Okay. So if you pick any proper subsequence, right, it converges actually faster. Okay, but the limit point, but the conversion point is not living inside the Y. Okay, so the open interval 0 to 1 is not sequentially compact. Okay, but how about open cover? Still remember or not? Whether this is compact under the open cover sense. Every open cover has a finite subcover. Is it compact in that sense? Also not, right? Okay. So actually from this case, right, we make some observation that actually in a metric space, limit point compactness, sequential compactness, and the first ever compactness that we define in this class which is the open cover compactness, which we short form to a compactness, actually are equivalent. Okay, so in metric space, these three things are actually the same. I think, are we going to show it or not? Let's see. Okay, so, but in topological space is a bit different. So let's look at in the topology case. So there are two theorems that we want to see. First is if a topological space is compact, then it is limit point compact. Okay, so meaning if you have the open cover property, okay, then you have this infinite subset property. Next, if a topological space is sequentially compact, then it is limit point compact. Okay, so from these two statements, right, you can draw some relationship graph. Okay, so if you have compact property, or if you have a sequentially compact property, both of these will imply limit point compact. Okay, in the topological sense. Okay, I urge you to try and build this graph. Later, we'll build a very large relationship diagram, and after we finish this subsection here. Okay, let's do it. Let's do the first one. So how are we gonna do first one? We'll do it by via contrapositive. Okay, so meaning want to show that if a topological space is not limit point compact, then it is not compact. Okay, so not compact, not limit point compact. So let's do it. Proof by contrapositive. Okay, suppose X is not limit point compact. Okay, so just use definition. So meaning there exists an infinite subset A of X which has no limit. Okay. So now how to link to a open cover thing, open set. How do you cook out an open set here? Okay, so the next claim is then for every x in S, every x in X, with the X, there exists an open neighborhood of X, okay, such that this open neighborhood intersect with the infinite subset A here should contain in the singleton set containing X. Why? Meaning what? What this means? This as a subset of a singleton. Either this set contain X, or this set is the intersection is empty. Okay, why is this true? What if this thing contains something else? Sorry. Yes. Okay, so if this is not true, then X will be your limit point. Okay, otherwise X will be your limit point. Okay, so now, so let's continue with this UX here. So we have UX for every X. Huh? So now, if we take all such possible UX here, okay, then this is N, actually N open cover, okay, of X. But then, since each UX here will cover at most one element of A. Okay. Then any finite subcollection of C cannot cover the infinite set. Okay, so C has no finite subcoupler. Okay. So from that intersection, that intersection property is pretty important. Either you contain X or either you don't. Okay. For each unique UX here. Okay. So if you take one UX away, no one can cover that X anymore. Does it make sense? Okay. Should we prove the second one? It's not too long. Let's do it. Okay. How about second statement? So second statement, I want to show sequentially compact implies limit point compact. Okay, so this time we'll do a direct proof. So let's suppose X is sequentially compact. Okay. Limit point compactness, what's the definition again? About infinite subset, right? So every infinite subset of X here has a limit point in X. Okay. So let's take arbitrary infinite subset of X. Let's call it A. Okay. But now you have an infinite subset now. Okay, but you have a statement on sequentially compact. So how do you apply sequentially compact here? What's the key, okay, to turn on sequentially compact? Every what? Sequence, right? Okay, has a convergence subsequence. So you need to start with a sequence. You got an infinite subset here. Can you cook out a sequence or not? Huh? Just randomly cook out. Okay, but now A must contain a countably infinite sequence an of distinct terms here. Okay, so you just take an infinite sequence out of this. Then what's next? Sorry, we got yeah, okay, got a subsequence, okay, that converges, okay, to a point in A. So by assumption, this sequence here has a subsequence, let's say A and K lah, okay, has a subsequent converging to a point. Have we used A yet? No, right? To a point, let's say P or L. Okay, L in X. Then what? What's your goal? What's your goal? Limit point compact. And to show that every infinite subset A has a limit point. Okay, have you found the limit point yet? Huh? L. Okay, L why L is a limit point of Y. Convergence subsequence. Make a ball. So if you make every open neighborhood around L will contain something other than L. Okay, so this thing is very important. Distinct term. Distinct term. We cannot have like A1, A2, A3, A4, Y. Okay, so it must be distinct. Okay, why we can do that? Because we start with an infinite subset. Okay, if you say that, oh, I cannot find 老师我找不到这样多, then you are not start with an infinite set. Okay, does it make sense? Okay, so actually, uh, so let's conclude it. So hence, Y, so L is a limit point of A. Okay, so you check the limit point definition. Okay, and together, yeah. L in where L in wait. Oh yes, yeah, yes. Thank you. Okay, check limit point definition and the distinct and use distinct term assumption. Okay, all right. Right. So do we have the other direction or not? Okay, so we have one implication, right? Okay, for both statement here. Do we have the other implication or not? So I will give you an example that limit point compactness doesn't imply compactness. Okay, so let's look at one example such that limit point compactness doesn't imply compactness. Okay, so let's look at Z. So let's give Z the topology specified by a basis. Okay, so the basis is this two term set here, two element set. Okay, 2n and 2n plus 1 for O(n) set. So how does it look like? Can you imagine how it looks like? How does it look like? So I'll try and bring your real number line up. How does this look like? Wait, Zhao Shen, Zhao Shen still sleeping. How does this look like? 1 2 then 8. Okay. Even odd, right? Okay, 0 1, and then 2 3, and then 4 5, -2, -1, and then -3. Okay. Sorry. Sorry. 不是，也不是。I mean, okay, wait. Okay. So, 这样子的话也有道理在的，就是 like, if you want to view it as a subspace topology, right? If I view Z as a subspace of I need to take open set in R and then intersect with Z. Okay, so maybe if you like, you can think of a bit larger open interval that contain -2 and -1, and then I intersect with Z. Surely I get this two elements there, right? Yeah. 你可以这样想，如果你不要这样想的话，或者这条线没有其他的点的话，只有 Z 的话 I'm just like try to group the two elements together. Okay. 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 So the claim is this basis, right, is an open cover of Z. Okay, I cover everything already, but there's no finite subcover. Make sense or not? If I remove any one of them, then no one cover the two elements anymore. Okay, so this space is not compact because I produce you one open cover that doesn't have a finite subcover. Okay? If you want to prove it is compact, you need to show that every open cover has a finite subcover. Okay, so Z is not compact using the open cover by B. Okay, but what's the second thing I need to show you from my slogan here? I show you not compact. What's the next thing I want to show you? Hey, what do you think? What's the next thing I want to show you? I show you not compact already. So how to echo the subject there? Two choice only. I want to show it limit point compact, or I want to show it is not limit point compact. And make a decision. Yes, we want to show that it's limit point compact, but it's not compact. So how to show limit point compact? To show limit point compact, I think you don't have other method, right? Just go for definition. Okay. You need to discuss for any infinite subset. Okay. Discuss any infinite subset. So second part. So given any infinite subset A of Z. Okay, we want to show that it has a limit point. How to show it now? It has a limit point. one thing I want you to observe here is the open neighborhood of one point here is really not that many choices. Not many choices. Okay. There's not many things you need to check here. Because to check limit point, you need to check for every open neighborhood, right, of that point. Okay. For example, okay, open neighborhood of -1. Could it be this or not? All the open neighborhood must contain the set, the two element set -2, the two element set containing -2 and -1. Okay. So the claim is if 2n is in there, okay, who is the limit point? Right? So meaning what? You need to stand at the limit point, build your open neighborhood, must intersect A other than yourself. I tell you, inside A got 2n. This is one thing that you can intercept. Which open neighborhood can intersect 2n? Your basis looks like what? 2n plus 1. Huh? Okay, so if you have 2n inside your set here, then the claim is 2n plus 1 is your limit point. Okay. So your open neighborhood of 2n plus 1, right, must contain 2n. Make sense? Any open neighborhood of 2n plus 1 must contain 2n. 绑在一起了 2n plus 1 and 2n 绑在一起了 Okay. Live in A. Does limit point have to live in A or not? Oh. Wait, oh, we want to show limit point compact, right? Let me see. Let me see. What's the limit point? Yes. Oh, okay, good. That's a very good point. That's a very good point, actually. People will confuse. As a very good point here, where this X live in is pretty important. Pretty important here. Does limit point live in Y or live in X? Let me see. Limit point compact.
Calculation shows this lives in Y, but now we should be as the subset actually. So it's which is the whole space as a subset of itself.
Say again.
I mean, when this definition is lives in a limit point in Y, but when you do that example, you just consider the whole space. So
Yes. Yes. Okay, so people will confuse sometimes they think that this Y have to be A. Okay, so please be reminded where your limit point or the point that you converge live is very important. Okay, so there are few spaces appear here. They are the original space. Okay, they are the subset. Okay, and then there's a candidate that you want to check here. Okay, so where this limit point live is very important. Don't confuse yourself. Okay, so the subject that we want to discuss is actually a subset of topological space. Okay, and then you look at some infinite subset here. These two cases are both infinite subset. Just that for sequence we need to arrange them. Okay, And then where this thing converge to, or the limit point, it just have to live in the subject that you want to discuss. Okay, whether you want to decide it is whatever compactness is. Okay. The topology.
Maybe that will, I mean, you give them basis, right? It's not clear what all the open sets are.
Yes. So do anyone still remember what's the basis? How does all the open set looks like for topology generated by basis? Union. Okay, union of these basis element. Yeah, we proved that in class. No, just you. Just you. Yeah.
Yeah, so intersection of two bases are still an open set, right? I want to describe almost the open set. But empty, but if you want to describe a set of sets, then it takes focus with you. But
Yeah, but we can write it as a union form. Okay. So this is how about the other cases? Okay, the other cases, if you have 2n plus 1 inside A, okay, can you guess what's the implication here? Then I can pick another partner, which is 2n. Okay. Okay, either one of this case must exist because your set is infinite, and then Z is either even or odd. Okay, so thus the space is limit point compact. Okay. All right. I will recall one of the similar proposition coming from a metric space, and I won't do it in class. Hopefully, you can go back and do it for uh, general metric space here. Okay, using the definition. I think we do it for Rn, right? Well, let's bring down the. Okay, this one. Okay, so these are the familiar property coming from Rn. So first, a limit point of A need not be a member of A. Just now we come across this. Second, if X is a limit point of A, then every open ball centered at X contains an infinite number of points from A. Okay, so you can use the every open neighborhood to build this infinite number here. Third, I think third you are very familiar, right? We have a midterm on this kind of thing. So A is a subset of A, the closure of A. Every point in the closure of A is either the limit point of A or an isolated point of A. Okay, but not both. They cannot be yeah, but not both. Cannot be limit point and isolated point at the same time. Okay, because if you are limit point, there are infinitely many things that approach to you, right? But isolated point, there is just an open neighborhood such that you cannot see other member. That's why you are called isolated. Okay, last one is X is in the closure of A if and only if every open ball, okay, of radius r around X contain a point of A. Okay. Okay, this is just recall. Let's see. So, what time is it? I think this is the last one we should do here. Okay. So we'll prove this statement here. So we're gonna establish in a metric space X. Okay, so this is not topology, this is metric space in the metric space level. Is a limit point compact if and only if it is sequentially compact. Okay, So in our relationship graph, right? So just now we have limit point. Hey, sorry, not limit point. Hey, compact. Wait, my brain is like a fish brain. Okay, so compact and sequentially compact. Okay, implies limit point compact. Okay, so these are on the topological level. And then we see that we cannot go back from limit point, limit compact to compact just using topology. But we can go back and forth using just a metric or sequentially compare limit. Okay, let's see this proof here. This proof is actually quite fun. Okay, quite fun. So one direction we already get, right? Which direction we already get? Huh? Which direction we already get? So theorem sequentially compact to limit point compact. Okay, because metric can induce a topology. Okay, using metrics we induce a topology. How to use metric induce a topology? Yes, you use open ball as your basis. Okay, that's how we say something is open in the metric space. Okay, so what's left to do is we want to show that a limit point compact imply a sequentially compact. Okay, so here really we need to use something special for metric space. Yeah. Hey, why tower? Sorry, I see. This is not fish brain anymore. When I think people mention about fish brain is about their memory, right? Yeah. Huh? Okay. 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 Suppose X is limit point compact. Okay, we want to show that it's sequentially compact, right? So then you need to check for every sequence too. Okay. So then take any sequence. Xn. Next. Okay, I want to show that there's a convergent subsequence. I want to show that there's a convergence. But this is arbitrary sequence. Okay. So what could this sequence look like? If this sequence already converged, then you are good. And the whole sequence is a convergent sequence for you. Okay. So one case, one easy case could happen is if you just mesh these sequence together. Okay, so this is a very technical way to put things. So if this set here is a finite set, okay, so meaning there's infinitely many term get sent to the same place, right? Okay, this is what is this called? We can use the pigeonhole principle. You have infinite many terms. Okay, but if you looking them as a set, right? Last time we mentioned that set will only distinguish different element. Okay, but you got infinitely many terms of. So pigeonhole principle says what? What do you mean? No. There's two things here. One is sequence, one is set. You understand what I say? Maybe I give you an example. So let's say your sequence is like 1, 2, 3, 4, 5, 5, 5, 5, 5, 5, 5, 5, 5, 5, 5, 5. Okay, but what's the set? 1, 2, 3, 4, 5. Can I put another 5? It's the same 5. Okay. Okay, so pigeonhole says that then one term must be repeated infinitely often. Okay. Then this is a good subsequence they want to look at. Okay, because this gives a constant subsequence, but constant subsequence will converge. Okay. Well, okay, so we disregard this case. Okay, after we disregard this case, we want to build another convergent subsequence. Okay, so suppose then A equals to this set of xn is infinite. Okay, if it is finite, then we have constant subsequence. Okay, otherwise it's infinite. Right. But this is an infinite set, right? Okay, we have what property we have? We have limit point compact. Okay, limit point compact, that means what? You give me an infinite set, I give you a limit point. Okay, so then A has a limit point. Okay, but from the previous proposition that we recall just now, we see that not only does every open neighborhood, let's say open set, U that contain this point A must intersect other point other than A, and also this intersection must be infinite. Okay, just now the proposition we recall. Okay, so there are infinitely many elements inside one of the neighborhood. So what we can do here is, we do here. So let's pick this. So we're gonna build convergent subsequence. Let's see how we build it. So let's pick A1. Okay, in the ball one with radius 1 uh, centered at A. Okay, and then obviously we don't want to pick A itself. Okay, otherwise you say I'm cheating, right? Okay, so we can pick this. Okay, because there's infinitely many things there. Since A1 is in A is what? Still remember what it's saying? We just collect all the Sn together. So meaning what? A1 should be equals to xm1. Okay, for some m1 here. Okay, don't know which one, but never mind. Okay, then how to build the next one? How to build the next one? Do I repeat the step? Okay, I just pick A2. Okay, in a smaller radius ball around A. Okay, I want to converge to A, right? Okay, and then also I don't want to meet A as well, such that A2 is equal to SM2 for some M2. Is it enough? Huh? Enough, Lydia? Enough or not? Cannot be SM1, first of all. So is it enough to just set I don't want to meet M1? You can do that, right? Because there are infinitely many things there. Is this enough or not? Why not? we want to have a further point in the sequence because we want to build a subsequence. Okay, so this M2, right, should be really greater than M. Okay, then we continue. Okay, you look at a smaller and smaller ball and then try and find a further term in the sequence. Okay, so the general term is like this. So we're just picking AJ such that it is in the radius of 1 over J. Okay, around A. Obviously, this one intercept. I don't want A. Sorry. Yeah, I don't want the limit point A. And then I also don't want everything else from everything else from is this a nice way to write it out? Let me see. So x1, x2, blah 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 blah, up to the A1 that you pick up. And then in the middle, you also don't want up to the A2 you pick up. Okay, and then so on. And all the way up to the previous AJ minus 1, 2. Okay, you don't want to pick from all these. You can do that because this neighborhood must contain infinitely many elements there. Okay, so we define a subsequence an of xn, which, so in this case, because by this construction, right, the ball is getting smaller and smaller. Okay, 1 over n, which clearly converges to. Okay, any question? Any question? So from here, you also can see the subsequence, right? Okay, so your sequence is like x1, x2, up to this guy is some a1, a1, xm1, right? Okay, some number. And then why subsequence? Because you pick another a2 from a further term in this original sequence. You know, this is just a truncation of Sn, S1, S2, 3, 4, 5. Yeah. Any questions? 有问题吗，Lydia？ truncation 啊，切掉，truncate. So you stop at a certain end. So you got an infinite sequence, right? You chop, stop at certain end, truncate. Any question? OK。你看一下你们的朋友还在睡觉，call 一下，还没有来上课啊？call 一下招生，他在吓我。OK，OK. In that case, let's break until 11:10. Yeah. 是。应该就很好。对啊，电话你open ball，如果我拿 open ball 的话，我不够 generate，我需要哪个 section？不是每个 open set 都找效的。你现在是在问我 basis 的 definition 啊，还是 basis 的 definition？你 basis 有 definition？对，但你刚才是 define 一个 subset，然后你拿 subset 来 generate topology。啊，对，它要符合一个 basis 的 definition，不需要，它只需要 define 那个 generation 就可以了。诶，你只需要拿全部 union of all finite intersections 就可以了。这种 generate 方法是另外一种，那是 sub basis。不是，随便给一个 subset，你就可以 define 一个 topological space 啊，such that 你的那个 set 就是一个 basis。basis 的 没有在想一下讲什么。
就是应该是我反正我随便给你一个，我给你一个 set act，然后我选一堆 subset，
对对对对，没错。
它都可以 generate 一个 topology such that 那个 subset 是一个 basis。
OK，我知道你讲
那个
什么
basis 有 definition 对不对
，basic
？definition 是给
definition，
你一个
对
subset 不了，但是我有一
对
个 subset，我 generate 一堆 set 出来，
，OK，但是
然后我叫他们 open set，然后这个 set 一定是一个 basis，一开始的 set 是一个 basis。
我要跟你讲的是，你有两种方法 form basis，其实
但是如果你一开始没有 topology 的话，我不知道 basis 的意思是什么。你 basis 只能知道你给我一个 topology 之后，我才跟你讲。
它没有，你不用 topology 就可以有 basis 了啊。那个 basis 的意思就是来每一个点都要活在一个你选的东西里面
OK
选的一个 subset 里面。
OK，
第二条件是每两个的 intersection 如果有东西活在里面，你选的东西，你选的东西要 such that 它会活在他们的 intersection 里面 contain 那里一点，它不一定要是那整个 intersection。
对对对，但是 intersection 就可以了，对不对？
它是活在 intersection 里面就好了，
对对对，
不用整个 intersection。
嗯，
content 就可以。比如OK，open board 的example 就是来如果你说我要用 open board 做 basis，其中一个方法是你 intersect 过后，把那个 intersection 也加起来叫它 open，或者就是你只要 make sure 那个 intersection 里面还有一个 open board content 里面的东西就好了。它会分不同的 basis，
它会分不同 basis，
不同 basis。如果你
不同 basis 不同 open set 吧，还是因为我刚才是讲的是你给我一个 basis，我要找 the set of all open sets 的话，需要用 both union 跟 finite intersection，
不用用年吧，
所以
你的话，
啊，basis
它是两话这边可以查。
哦，你们的 basis 本来就 contain 全部 intersection。哦，你们 OK OK，这样你们 definition 用跟我不一样。
对，因为你讲的那个是叫做 sub basis。如果你要把 finite 再加进去因为你可以想象 open ball 如果用你的那个方法做出来的话，它的 open set 有时候不长这样。
对啊对啊，就是我刚才讲的，我随便换了一个，
我不可以这样子讲，
那个东西就不是这个东西是它不远啊，对啊，它不远，exactly。
我也不可以讲它不远，因为 uni open ball 可以做出四方形的东西吧，就是 like 那一个 part 也是你的，也可以变成你的 basis 的一部分呢。就说你 basis 的一部分可以不是圆圆的东西这样子，这样应该比较对。那会比较 fine，比较 fine，更多，因为你把那个中间那种东西都加进去，之前只是
对我来讲，上杯是我会觉得是比较 cost，我只是选 base 里面的一些小东西来 generate 剩下的东西。没有，这 definition 你应该要给他们做叫什么，你知道吗？给他们all positive all finite set，好像是3个的 equivalent，对不对？只要我的 topological space 是一个 finite set，
OK，
对吧？然后
finite set 的 topology 要放吗？我知道你讲嘛。
很好的问题。我的 claim 就是不管你放什么 topology 都应该要对啊。
OK，对，是吗？我没有想过。
应该是要你找看，不然的话你叫他们做一个 counter example。
他讲全部 finite set，不管你放什么 topology，这3个 notion 也是一个。
这2个意思
2个还是3个？
至少有2个，我看到2个，觉得至少有2个，
就是 limit point 跟 sequential。
对，应该是或者 compactness 也是，因为 compactness 就 free 了嘛，compactness 你只有 finite 嘛。
OK，
所以应该是3个，其实说不定真的是3个。
这个我没有想过，可以 try 一下。所以你是讲 finite set topology 像 matrix space 吗？
I mean 不能讲到像 matrix space，对，它比 matrix space 更简单。
更简单。
对啊，finite set 啊，compactness 永远都 free 的那种。点啊，
几个点？怎么？有吧？有。
肯定是好那个。
啊，开始问你一个那个证，哪一个证明？就是那个 sequentially compact to 那个 limit compact 那个 sequentially compact to limit B，OK，一个嗯，诶，哦，这个跟那个 notes 不一样，为什么？哪一个 note 不一样？我的 note，对对，哪里不一样？这一份不是，就是跟那个打的，对，打的，对，打错了，对对，而且错了不止一处。看一下，他们在修改，那个是去年打的，给我看一下。如果你之前你有找到有问题，不是，你可以发给那个同学要到这，这是发给啊，对，对，但是我刚刚教的是去年打的，但是你也可以告诉他这样，让他注意一下。
没事，我自己读的时候也读出来很多问题。
你也是个照片啊，
知道。
过了。
发现有一个地方把 given 都拼错。
for x，然后你这里写 for x，哦，就所以这个就有点看不懂，看不懂这哦，
吗？
OK，
和 each 和 for all 不是一样的吗？
不是，他讲这个 x 活的地方不一样。对对对，就感觉这个证明就不通了。OK，好，你可以跟那个赵正说的，你懂谁是赵正？就是这个从 Teams 上搜。对，那个证有个 OK，我改上 X，我回来看。OK，好，OK，要到你要 video 吧，老师？video 先放出来还是
我还有剩你多一个，你不要先就会找回来。
直接拉过来播就可以了？哎，sorry，搞错了。
是。
还有多一个是 break 出来的。
了解。
第二个，
这个是USB。我 test 一下声音。哦，这个只是图片哈，这图片哈。
对，
我看你拉过去就可以了。
哦，还是我可以放左右。
左右是意思是，可是我是 extend 哦，还是你是放在那边左右？没有吗？左右。这样子啊。
对，我要放在那边左右的话，就会放。
对。
哦，这样。哎，脚拿过去。对，这边。放。哎，我按不到，我放。可以。那也要看韩国。讲好话是。
那个
哦，
这个字哈。
这个很像做那种人放在那边。
哦，
试看。有，因为少人嘛。
你们会吗？
来，
我
来这边会。哦，这你电脑不能。对呀，我也是觉得有奇怪的。哦，还可以直接这样子啊！哇，
把文再拉去
关掉啊。
左边。
对对，
那谁要照片的？
那个有点小，看到。
怎样变成左右
你去啊？
？Press up, yeah, yes.
Shortcut key。
没有，他说你不同开的。我忘了，我的刷卡机是跟他不一样，是不是？叫先给我把这个，不然的话这边这样子也可以啊。我就是得把这个，可以直接看在过头吧？好像也不行
点它，还是要download？
，download 也可以。刚刚，那我我的头要歪了。
因为招商还没有进来。猜，那长应该是这个，
我
你
快点
是简
吧。
单的。哦，你应该要算有几双鞋。
2双，哎，是双鱼的。
我背了很多颜色。哦，哪个人他能把人家的考卷怎么点？
OK，可以了，
可以吧
？OK，
可以吧？
可以。
Okay, so we will start the sharing soon. Okay, so I will invite my friend here, Edmund. So Edmund, we were undergrad in ANU before, so we studied together for 8 years. We were closer when we get PhD because we got the same supervisor. Okay, so he is now researching in Sydney, okay, University of Sydney. So after this presentation, if we still have time, maybe you can ask about his experience. Okay, how is it life as a researcher, and then how Max influenced him. Okay, your time.
All right. So, so my teaching asked me to give you a talk about things that are related to my research. And since you're learning topology, then in fact, it's actually closer to my research than what I was talking about yesterday in some sense, because I don't really do algebraic geometry, but topology is definitely one of the things that I study a lot. Potentially, well, perhaps not weird topologies like metric spaces and things which are actually house of, which makes my life slightly easier. And in particular, I studied something called braids. And hopefully everyone here kind of know what braids are, right? And I'm not kidding. I mean, this doesn't, when I say braid, I really mean something like maybe on the right hand side is what you'll be more familiar with. Literally braids, okay? And braids are mathematical object. A lot of mathematicians care a lot about it, and it's a big topic in mathematics because they're related to a lot of things. They're related to knots, for example. Knots are, again, literally just knots. And in fact, they can be used to describe everything that is three-dimensional in the world. Kind of crazy, but that turns out to be the case. Every time when you take a knot, you can embed it into three-dimensional space, cut out that knot, and whatever you're left with can be used to describe everything that exists in the world. So I'll first try and tell you a little bit about what I really study about braids, try and describe the mathematical object to you, and then maybe give you 3 ways of thinking about them. And then finally relate to something that is slightly more topological, which is what we call the fundamental group. Okay, so maybe what I'll do, I'll play the video on the right-hand side because whatever I'll play the video on the left-hand side, and whatever that's on the right-hand side is more familiar to you, right? I think we all agree that whatever that's on the right-hand side is a braid. Okay, and I want you to convince yourself or try and find some sort of similarity between this thing here and this thing here. Okay, so let me just play this video. So the video is 49 seconds long, so you have 49 seconds to think about how they're related. All right, there you go. Okay. And that's about it. All right. Can someone try and make a good guess? I don't need a formal answer. I mean, nothing's really mathematical yet, right? I haven't give you any definition, I don't have anything. So just give some sort of intuition. I mean, we're doing mathematics. Intuition is very important. Can you see any sort of similarities between this video right here, the process right here, versus whatever that was going on the right hand side of the picture? Twisting, yeah, great. We see some sort of twisting, right? Any other ideas? Amazing. Yes, that's also one great observation. Anything else? So since you already mentioned the crossing part, so let me go to this video right here, and let's go slightly further on. So focus on 2 prongs each time. Are the directions actually the same? Like think about clockwise versus anti-clockwise. What do we see? Are you convinced if I say that 2 of them rotates like a clockwise action, and one of them does a clockwise thing and the other one does an anti-clockwise thing, right? So now, if I go back to this picture right here, what do we see? What do we see in terms of the difference between the crossing? One of them is on top, right? So one of them I do left above the middle guy, and the other one I do right above this guy. Do you agree? So one of them is like the crossing, which takes this 2 thing and then twists it this way. So this one goes on top, right? And the other one is going to take the right hand side one and then twist it on top of the left hand side. Can we all see that? Right? Focus on this picture again. Focus on 2 strands at a time. This one I'm going to do left above right. This one I'm going to do right above left. Right?
So you are kind of viewing the braid from the bottom.
Exactly. So now I'm going to use a bit of your imagination. Think of top to bottom as a plot of time. Okay? When I do this motion, right? So one of this motion here is basically just doing this mixing. Okay? But if I plot it against time, what's going to happen? It's going to do this break here. Right? Maybe let me just use 2 strings to show that. Right? Let's start with this. If I think about not doing anything, as time flows, it stays this way. Right? But afterwards, if at some point I decide to twist one or to the other, something like this is going to happen. Okay? Depending on whether I twist, depending on whether you from the top or the bottom, either it goes clockwise or anti-clockwise, which goes the other way around. Okay? And in fact, the study of braids can come up with 2 different ways like this. All right? One way is you really just literally picture them as time flow, and then all you're doing is just braiding things together. And the other one, you're thinking about it as by 3 prongs on the plane, and I'm doing some sort of mixing process. Yeah, and these 2 things describe the same abstract mathematical object called a braid group. Okay, so for the braid group, all of you, has everyone here taken the course in group theory? Yes. So, and we all know what generators and relations are, right? So in fact, it's a theorem that goes, do you have a... So it's a theorem by someone called Artin, Emil Artin, that basically proves the following. So BRM, actually, since we're doing 3 strands there, so let me just do BR3. It's called the braid group. And as a group, it is described by the following things. Okay, it has 2 elements, 2 generators, sigma 1, sigma 2, right? And it's generated by exactly the following relation. It says sigma 1, sigma 2, sigma 1 equals sigma 2, sigma 1, sigma 2. And that's it. Okay, so as a group, it's very easy to describe. Can someone tell me why whatever braid that I've drawn you there feels like a group? Sorry? So first of all, what do we need for a group? We need, sorry? Closure. But even before that, I need an operation on my set. What do I need? A binary operation that feels like a composition, right? Can you imagine how can I compose two braids? So if I give you, so let me draw something. So let's say, let me do the example there, right? So the first example does something like this, right? And then in the second step, it says, sorry, in the second picture, it first do one twist, and the second step, what does it do? It does this instead. Hopefully I drawn it correctly. Did you just see how I just perform a composition there? All right, I started off with this element, and then I compose it just by sticking more braids at the bottom, right? In fact, give me any braid that you like. As long as the number of strands are the same, I can always just compose it. Are we all happy? Okay. So, in fact, what I'm going to do is that I'm going to call this guy sigma 1. And just by convention, left to right, left on top of right, I'll call sigma 1. And right on top of left, I'll call the inverse. Okay, and this one does it on the second two strands. So I'll call it sigma 2 inverse. Okay, so first thing, convince myself. If I do sigma 1 inverse, what should happen? I want this to be the inverse, right? Literally the inverse. So I want this to really be the identity braid. Okay, what do you think the identity braid looks like? Just doing nothing, right? Thinking about it in terms of the process of mixing, identity means do nothing. Okay, so this guy. Okay, what about sigma 1 inverse? So let's use the convention that I've come up there. So sigma 1 should be this guy. Okay, what about sigma 1 inverse? Should be this guy on the top, and then this guy. If I pull this straight, what happens? It becomes a straight line. Okay, and if you have ever braid your hair before, you know that this is a bad operation to braid your hair, because if you do this, clearly it's going to fail, right? You're not going to create any braids, and that's the whole point. All right. So these two things are the same. Do we all agree? Okay. Give me a result. Okay. So what's the last thing that I'll convince you? I'll try and convince you that this relation here really holds. Okay. Of course, actually, if you've seen group theory before, then you would know that actually, if I give you some random group, producing like the producing the group presentation for it is quite hard, right? Defining some sort of subjective map into it is quite easy, but producing the actual like isomorphism is quite hard. But at least I'll convince you one of the direction. Okay. So the next thing that I wanted to show you then is just this guy. So what is sigma 1, sigma 2? Sigma 1 equals to sigma 2, sigma 1, sigma 2. Okay, I'm going to draw it first, and then I'll let you convince yourself that it's actually the same thing. Sigma 2, 1, 2. Can we see why they're really the same thing? Oh, I've drawn my braid wrongly, didn't I? Something's wrong. Always left. Okay, now I think this is okay now. Yes. Can we see why these two braids are the same? Especially people who braid their hair a lot. Okay, so let me give you a hint. Let's focus on this strand here. Okay, and let's focus on this strand here as well. Can you see the picture now? If I really focus on the middle strand, I can take this middle guy, swing it over to the other side, and I get exactly this picture. Okay, so this strand and this strand just lives in the middle, right? And then the middle guy can swing over both ways, and this exactly gives you this relation. Okay? Of course, proving the other direction requires a lot of work, but at the very minimum, you can see that this is a well-defined operation in the break. Okay, are we all happy up there? Right? So it seems like all I'm doing is drawing, right? And in fact, that's really what I research on. I could draw a lot of diagrams, and I can't really count, but I can draw pictures. But where is topology, right? I mean, it's a topology class, and Keesing asked me to talk about topology. But where does topology really come in? Okay, and that's what I'm going to try and convince you with the last description of break groups as some sort of topological operation. Okay, all right. So in topology, you haven't really learned this yet, but in topology, we care about spaces up to homotopy equivalence. And what I mean by that is just, for example, I want to tell a difference between a sphere versus a donut. Okay, I want to tell a difference between something like this and maybe something like this. Okay. And the best way to tell apart two different spaces is again to come up with some sort of invariance for that. Okay. For example, if I give you, okay, so here's a non-mathematical question then. What can you use to deduce that Keesing and I are different? I'm not trying to be philosophical here, but something very simple. Right? You can do a lot of things, right? I mean, you can maybe say something like, well, a more physical way to say that, well, Keesing is literally sitting right there, and I'm sitting right here. We're in different points, and if we're the same person, we can't be at two different points. Okay, then maybe you're saying, okay, maybe quantumly we can be somehow at two different points at the same time, whatever. Okay, then let's do something else. Okay, maybe Keesing is wearing a different shirt than I am, right? These are all invariants, right? You agree? Like you look at something, you say that, okay, well, I can deduce something that is definitely true about the person, definitely true about the other person. Compare them. If they are different, then they cannot be the same, right? With topological spaces, you can do something. All right. Of course, there are tons of ways that you can try and convince yourself that a sphere is not a donut. But here's a very naive way and very mathematically precise way of doing it. Draw any circle in two of these objects. I claim that one of them, no matter what circle you draw, I can always continuously take that circle and squeeze it into a point. You see how? Right? So think about drawing a circle in a sphere. Right? I can either draw it as a meridian, something like this, or I can draw it as something like maybe just lying on top of this of the sphere. And I can continuously deform this so that it becomes a single point. Right? Just by doing smaller and smaller, smaller, smaller circle. Okay. Similarly, with this big diameter meridian circle here, what do? I just take it, push it to the top, 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 and then slowly squeeze it, and then in the end becomes a point. Okay. There's a precise mathematical term for this kind of operation, and we call it the homotopy. Okay. For the time being, all you need to know is the following: two circles. So two things are homotopy equivalent if I can continuously deform that, so that at no point that I'm trying to jump from one thing to the other. Similarly with braids, we say that these two braids are the same because I can just continuously deform them by pulling one to the other, right? It's a continuous motion, right? I can slowly move this, move, and then it comes. Okay, so that's one way of thinking about homotopy. Okay, so let me try and make this slightly more precise now. Oh, actually, before that, no, even before that, can you see why this thing has a circle that I can no longer deform? I can no longer make exist at least one circle that I can't just take it and squeeze it into a point. Right? I've drawn you two examples, right? So if I take this guy here, think about a donut, right? And I put a ring over it. No matter what I do, like I can kind of like move it around, but I can never really squeeze it into the middle, right? I'm sorry, maybe I should be precise and say that the inside of my donut is empty. Okay, I know that if it's, of course, if it's an actual donut, then I can like squeeze through the donut and then it's gonna get crushed and that's it, right? But I want this to be a tube. I want this to be like a tube that is glued together, right? So the inside is empty. I can't go through the space. That space doesn't exist. Okay, and so let me try and again define something slightly more mathematically precise. With the black box that I'm not giving you what the definition of homotopy is, but again, just remember homotopy just means that I can continuously deform them slightly. Okay, so definition: the fundamental group of a topological space X, okay, is denoted by pi1 of X. And usually here, always want to fix a base point. So let me say fundamental group of a topological space based at X. So this is just some point in my big space X, right? It's just defined to be all loops based at X up to homotopy. Okay. So currently it's just a set, right? It's just, maybe let me call this point X, just for the sake of it. And then all I'm saying is just that I'm going to take all possible loops. This loop, even something like this is okay, right? As long as it stays on my sphere. Okay. And this is what we call a fundamental group. Okay, so this is a set. Why is it a group? Can you imagine the operation on loops? So let's say that I first do this, and then maybe I want to be interesting. I'm going to do this. Is that still a loop? Yes, right? I mean, all I mean by loop, so all I mean by loop is just continuous map. Maybe I'll use rho. Continuous map from S1. S1 means a circle, the circle map space, into X, which is continuous. Okay. This guy has a topology, the standard topology. I'm not using anything weird. X is just whatever topology that you have. So to be more precise, I should have written X tau or T. I don't know what you use. XT or T, the topology. But I'm hiding that. I want to think of X comes with the topology. S1 has a standard topology. Loops just means a map from S1 into X. Okay. So if you want, think of this as almost like drawing a circle in the space X. And that's it. Okay. It comes to the composition, right? And now maybe one last thing that I want to convince you is that why is there inverses? Okay. So it's similar to this picture that I had just now, right? I know that I can do this loop. Well, not yet a loop. You don't see that why it's a loop yet, but I can always do the inverse, which is something like this, which does exactly opposite of what you were doing. So here's the same thing. So let's say I start from this point. I'm going to walk here and then walk backwards. Okay, so let me pull out that picture and see what it looks like. I'm going to start from this point. I'm going to walk here and then walk backwards. Okay, what does it look like now? I can slowly push this point away. All right, I can slowly do this and then do this and then slowly do a single point. Okay, so that's the homotopy process. Okay, I walk through my space and then I'm going to slowly return it back again. Right, so this is doing one loop and then doing the opposite loop, which is why it eventually becomes the identity. Okay, so I know composition because anytime when I have a loop, I start from one point and I go back to the same point. So if I have a second loop, I just do the second loop again. That's my composition. because of homotopy equivalence, I also have the inverse, which just tells me that if I have one loop that does something, I'm going to do exactly the opposite of whatever I have. And then that gives me the inverse. And then you can check associativity, so and so. And this does indeed form a group. Okay? And the claim is the following. Pi1 of a sphere, no matter at any base point that you want, my sphere is 2, this is always 0, or if you want, the trivial. Okay, so just with one identity element. Or maybe let me use identity to be more precise for you guys. Okay, because any loop that I take can always be squished into something trivial. Whereas pi1 of a torus, sorry, I said torus. Torus means donut in a mathematical term. Pi1 of a donut, an empty donut, is one copy of Z, because I can always do this loop and I can do it as many times as I want. But there's also one more circle that I can do that I cannot actually retrieve. Can you see where? Think about the outermost circle, right? Maybe this one here, or even the one that is in the middle. I can kind of push it outwards, inside, push it outwards, inside, push it outwards, inside, but I can never really squish it yet. So it turns out that this guy has 2 copies of Z as my fundamental group. Okay, so one for the one that is a ring along something. Okay, and the other one is just the outer ring that draws around it. Okay, and hence mathematically I can prove to you that, well, these 2 spaces are really, really different as topological spaces. Right? I can assign to it a fundamental group, some precisely defined mathematical object, and they both have different fundamental groups. Therefore, they must be different. Okay? Any questions about this? Things are not really precise, so feel free to ask questions. I mean, the whole point is that you should be able to ask something about them. Yeah, do you guys call circle S2?
But they use cost circle S1, but the cost here S3
S3? No, this is S2. S2, sorry. Maybe my writing is bad. S2. No, my 1 and 2 stands for the dimension. Of course, the sphere is embedded in 3 space, but yeah, my 1 and 2 is the dimension. Okay? All right. Maybe now my question for you is that, can you imagine how grades are actually fundamental groups of something? Right? So try and think about this guy here. So what am I doing every time when I'm taking a loop? I imagine myself as traveling against time and just do some sort of walking in my space. And then the only requirement is that I have to stop at the same point again. Okay. So let me describe the following thing. To think of a fundamental group, I believe this picture might help slightly more. Okay. So I want to first think of it as the 3 prongs that you have on your plane, the one that is doing the mixing. Imagine them as points in a plane. Okay, I'm just going to call my plane C. And I want 3 points on my plane. Okay, you can do R square if you want. Writing C is just me being lazy, so I don't need to write the 2 all the time. Okay, I just want a plane. And I want 3 points on my plane. I want to fix 3 points. Let me call them x1, x2, x3. Think of these 3 points as a point in exactly in this space, right? It's picking out x1, picking out x2, picking out x3, this space. And at any point in time, I don't want them to be the same. You agree? Right? Because my prong cannot hit each other. The first condition is that x1 okay. What does a point in this a fundamental group in this space look like? I take 3 points, and then I'm going to start moving them around. As long as I return to the same point, I'm good, right? It looks like a loop. Do you agree? Take 3 points, move them in C cross C cross C as much as you wish. As long as I go back to the same point, then I'm going to say that that is a loop, right? Because I start off with the point in here, and I'm going to start off with I'm going to go through some other points, I don't care where. And at the end, as long as I go back to the same point, it is a loop, right? It is a map from x1 to x, okay? So now imagine x1, x2, x3 sitting in some sort of plane, right? And now x1 is allowed to travel anywhere that I want, as long as I go back to the same point in my space, which is this again x1, then it should be a loop, right? So I can do the same thing for x2, as long as I'm in. Okay, and similarly for this guy, I can do whatever that I want. Maybe I'm going to be slightly lazy here. I'm just going to do a very simple procedure here. Okay. Hopefully you're convinced that this looks like exactly like a braid, right? And so the precise term for this is going to be the following. So the main difference here is that I'm allowing myself to go from x1 only back to x1, okay? So this is a set of ordered points because I really care whether or not this is x1 or this is x2 or this is x3, okay? If I really want to be precise, then I can define my space as the following. So this space is called the configuration space of 3 points, ordered 3 points in C. And by definition, it's going to be exactly x1, x2, x3. Actually, let me do it slightly different. I'm going to do y1, y2, y3, 3 points in C cube, okay? Such that at any point in time, y1 not equals y2, not equals y3. Okay, this is a topological space. To be even more precise, you can even do the following. I can actually do C cube minus away 3 hyperplanes. Okay, I just have to remove the hyperplane that says that what's the best way of defining this? Maybe I'll do the following. I'll remove 3 things. I'll remove h x1 equals x2 union h x2 equals x3 union h x1 equals x3. Okay, and I'll describe to you what each of these means. So h of xi equals xj is exactly all the points. Oh, sorry, let me use y again because I want to fix x to be whatever that's going to be. So y1, y2, y2, y3, y1, y3. And h of yi equals yj is exactly the points y1, y2, y3, such that yi equals y. Do you agree that this is a hyperplane? Right? In a complex linear space, this is a vector space, and I'm just removing the planes cut out by the condition yi equals yj. It's a linear condition, right? It just says yi minus yj equals 0. Therefore, it's a hyperplane. Right? And this, all I need to do, these two descriptions are the same. Try to convince yourself that they're actually the same thing. I'm just taking C3, all right, minus the hyperplane that's saying that, well, I don't want any points that where y1 agrees to y2. I don't want any points where y2 agrees to y3. And I don't want any points where y1 is equal to y3. Okay. And now pi1 of this configuration space of ordered 3 points in C is exactly what we call the pure braid group. By the word pure, pure just means that I'm not allowed to swap x1 and x2. Okay, so the braid group just now, remember that if I want to braid my hair, I don't always start from the first strand to the first strand again. I might go from first strand to the second strand. Right? Theo means here that my first strand always has to go back to the first strand, my second strand always goes back to the second strand, my third strand always goes back to the third strand. Okay. If I wanted a braid group, then we'll have to do something more fancy, which is called the configuration space without the ordered points. And what I mean by that is just that pi1 configuration space of ordered 3 points, mod out by S3. This S3 here is a symmetric group of 3 elements, which just says that I'm allowed to swap any of these points around. It's just a permutation group, right? S3 is the permutation group of 3 elements. Okay, if I mod out by S3, then this is exactly the braid. Okay. All right. So with the last 10 minutes, I'm going to pull off a party trick, which I thought was quite cool, and it relates fundamental groups in some ways to things that you may have seen or may not have seen before. Right? Let me do the following. I think I can remove this.
5 more minutes.
Yes. Hopefully I'll be fast enough. Okay, so take a disk and put 3 holes on it. All right, take a disk and put 3 holes on it. I claim that the fundamental group of this space at any point you like, maybe call this point X, is exactly the free group of 3 elements. Does everyone remember what free group of 3 elements means? It means exactly that as a group, it has A, B, C, and no relations. All right. In particular, remember that the free group is not an abelian group. All right. A, B is not the same as BA. All right. It's a free group, no relations at all. A, B, A, B. I can write any words, including A inverse B. A inverse B is again not the same as B inverse. Sorry, BA inverse, so on and so forth. No relation at all. Okay, it's just a free group. Why is it a free group of 3 elements? Can someone try and guess? Can you find at least 3 loops that looks completely different? Right? I can do this, and I can't pull it through, right? Because this is a hole. Or if you want to think of it as a prong, right? It's stuck there. Right? There's a hole. I can't pull it through at all. Similarly with this, and I'll call this loop with one particular direction, A, B, C. Okay, I need 2 volunteers, or maybe 3 actually. The 3 of you want to come up, or right? Be fast. I only have like how many minutes do I have? I only have like 3 more minutes, maybe. 3. I want you to imagine the following thing. I'm trying to hang. I want you to think of this as 3 nails on the wall. Okay, 3 nails on the wall, and I want to hang a picture. This point X is my picture, right? And I want to hang it in the worst way possible. Okay, 3 of you stand in a straight line. Put all your hands out. Straight line, hands out. Okay. I don't actually have a nail. I don't want to destroy anything in this university. So hands up. Nails, nails, nails. Okay, maybe closer. Yes. Okay. All right. And I want to hang my picture. What's the easiest way to hang it? Do you agree? This is how a normal person would hang a picture. Right? And no matter what I do, clearly this is non-trivial, right? Because I can't pull it through. Right? And what does it look like as a loop there? It looks exactly like first do A, and then do B, and then do C. So as a group element in that space there, it does exactly A, B, and C. Okay? And if I remove any of the nail, will it hold itself? No? It will, right? Because it's still do this. Okay, now let me try and do a trick. Put your hand there. Straight hand again. Let me do something weird. Okay. Seng, help me. No. Just help me check that my math is correct. Okay, let me do 2 first. Okay, so let me do 2, 1. Let me do first. Okay. I don't know if you can tell whether this thing is going to fall or not, but can someone make a guess? Yes or no? Is it going to fall? Yes. So it's not going to fall, right? Why is it not going to fall? The commutator is not trivial. All right, this is the first time I'm doing experimental mathematics, but let's go. Okay, we're saying, right? Now, remove that point. Do you think it's going to fall or not? 3, 2, 1. It's going to fall. Can everyone see what has actually happened? Okay, so all I've done is actually the following thing. Thanks, guys. I played this trick which says that my loop, I started off with a loop that looks like I first do A, right? So I do this direction, and then I do B. So I do the same direction, clockwise direction again. And then I'm going to do the commutator now, which is an amazing observation solved by him. I'm going to do this. I'm going to do this. Okay. As a group element, this is not the trivial element. If it was trivial, you should imagine this as the homotopy tells me that I can pull my string down and it completely vanish. Okay, I can squeeze it. We know that a free group does not have this relation, therefore it don't have some such a thing. But when I remove one of the nils, okay, I'm essentially saying that let me kill B. I set B to be the identity. If you really want to be precise, all I've done is that I've defined a surjective map from the free group to the group where B is equal to the identity. And then now what happens? A inverse, B is now the identity because my loop, right? Because if I imagine this as like I've removed my loop, I removed this guy. Now B is the identity because I can just take this loop and just squish it through. So B becomes the identity. Okay. And now this is just A inverse. And of course, we know that this is the identity and therefore it's collapsed. Okay. So since I do not have time to perform my tricks on 3 things, play around with 3 and come up with the following solution. I want to hang my picture in the worst way possible on 3 nils, such that every time when I remove one of the nils, it's always going to fall. Of course, this is the worst thing ever. You do not want to hang your picture that way. But just for the sake of tricks, try and find a solution for that. Okay, and hopefully this picture here gives you an idea of how to construct such an example. All right, is that good? Okay, I think that's all. So thank you.
Okay, thank you, Ed. This is a very good intro to algebraic topology. If you're interested, please join our class next semester. Okay, we're time's up now, so thank you very much. See you tomorrow.等下人，哎，我找不到我的 mouse。了。